global uppvärmning. Varför den är en så viktig motivering att vi måste hålla 1,5-gradsmålet. Det är som sagt en ära vara här. Och jag kommer att vara moderator för en panel av 5 excellenta forskare. Och jag kommer att säga några ord om vår panel nu och sen kommer vi snabbt gå direkt in på presentationerna. Jag kommer att byta språk fram och tillbaka, så när jag presenterar en forskare som är inte svensktalande kommer jag prata engelska och sen kommer jag byta tillbaka till svenska. Och då kan vi köra hela sessionen, alltså vi kan översätta för varandra. So the first panelist, and Rob, I'm going to present all the panelists first, so you don't need to jump in straight away. The first panelist is Rob DeConto. He is co-director at the School of Earth and Sustainability at University of Massachusetts, Amherst. Rob studies polar climate change, the response of ice sheets to a warming climate, and coastal impacts of sea level rise. Rob is one of the lead author of the IPCC's special report on ocean and cryosphere. And Rob's going to be talking to us today on melting ice, rising seas, overshoot, and Antarctica. Our second panelist kommer att tala svenska och hon heter Ingeborg P. Hon är en av våra yngre forskare och det är alltid jättebra som är en early stage career forskare och hon är glaciolog och arbetar mycket i fält. Hon har omfattande fälterfarenhet från Skandinavien, Arktis, Alperna och Anderna. Hon arbetar även med International Cryosphere Climate Initiative som outreach coordinator för Sverige och de nordiska länderna. Det kommer att vara väldigt intressant att höra dig alldeles strax, Ingeborg. And we have with us from Plymouth Marine Laboratory, Helen Findley. Helen is a biological oceanographer. She uses a combination of experimental, observational, and modeling tools to investigate the impacts of climate change and ocean acidification on marine organisms and ecosystems. And it's going to be interesting to hear what you have to say, Helen, later on. Tillbaka till svenska, och då har vi Gustaf Hugelius. Gustaf är tillsammans med mig vid Berlin Center för klimatforskning. Och Gustaf studerar markens roll i den globala kolcykeln med särskilt fokus på permafrost och torvmarker i arktiska och boreala ekosystem. Och our last speaker today will be Dirk Notz. He is Deputy Managing Director of the Institute of Oceanography at Hamburg. He researches on the role of sea ice in the climate system and on physical processes in sea ice. He's co-author of the IPCC's 6th assessment. To all our panelists, a great warm welcome to this meeting. And I would like to now welcome Rob DeConto, who's going to talk to us about melting ice, rising seas, overshoot, and Antarctica. The floor is now yours, Rob.
Perfect. We'll hope this works. Okay, I thought I would just give a quick update on recent work appearing since the SROC was published in 2019 on sea level rise. Okay, so first quick message. This is my colleague, Andrea Dutton. She's standing on coral reefs. There are about 8 meters above modern sea level. One is in the Indian Ocean, one is in the Florida Keys. The geologists are telling us that when the world was roughly about the same temperature as it is today, sea level was many meters higher. And that is telling us it's a clear indicator that the big ice sheets are sensitive to a little bit of warming. The current perspective on sea level rise, rising at roughly 3.6 millimeters per year, it's accelerating. The rate is going up 3.6 millimeters per year is about 2.5 times faster than the average rate of sea level rise over the 20th century. What's changed is an increasing contribution of land ice. In the 20th century, thermal expansion, the oceans gaining heat, getting warmer, was the primary driver. Now land ice has become, the contribution of melting land ice has become the primary driver. That is important, and it should be worrisome because there's so much potential sea level rise locked up in the Greenland and Antarctic ice sheets. This, as of 2019, was the assessment of the IPCC. This is from the SROC report. And don't worry about the graphics. To be quick, you can just look at these numbers. These are in meters of sea level rise. In the year 2100, under a low emissions RCP 2.6 scenario, the central estimate, the best guess as of the SROC report's publication, was about 43 centimeters of sea level rise. And you can see that in a high emissions case, it doubles. Now, if we have a longer term perspective out in the year 2300, there isn't much of a change between 2100 and 2300 in the low emission scenario. That's great news. But in a high emission scenario, like an RCP 8.5, there's a huge potential for sea level rise. And you can see that at the high end, this is the top of the likely range of the estimates, it's 5 times greater in the high emissions than the low emissions. So clearly, for sea level rise, mitigation is of critical importance, important message. You can see that in the long term, there's a huge uncertainty in the magnitude of sea level rise, and that, as you'll see, is driven by Antarctica. The Antarctic ice sheet is huge. It contains enough ice to be the equivalent of 57 meters of sea level rise. And just, you know, if those of you who don't work on this, here's the United States superimposed on the Antarctic continent for scale. We're talking about kilometers of ice cover on this massive continent. Now, Antarctica is fringed by floating extensions of the ice sheet flowing out into the sea, and we call these ice shelves. So snow falls in the interior, the snow turns to ice, the ice is heavy, it deforms and flows downhill toward the sea under its own weight and extends into these floating ice shelves. The floating ice shelves are critical because if they bump into something on the seafloor, they provide some structural support that slows the flow of the ice from the interior out into the sea. So what we're worried about and what we are observing is that these ice shelves today in a warming ocean are beginning to thin and they're losing their strength, in this buttressing support that's holding back the flow of ice from the ice sheet out into the sea is weakening. In places where that is happening, the ice is flowing faster into the ocean. So the latest generation of models that actually account for these very complex physics, and this is a great challenge in modeling this system, these are what I wanted to show today, is that this is a perspective looking from the year 2000 to the year 2100, so the 21st century. And just if we look at these red lines, this is the rate of sea level rise contributed by Antarctica in a scenario where we limit global mean warming to plus 1.5 degrees C, like a Paris Agreement aspiration. And what we find is that the rate of sea level rise really doesn't change much throughout the 21st century relative to today, if we're able to maintain warming at 1.5. In a plus 2 degrees C warming scenario, there's a little bit of an uptick late in the 21st century in the loss of ice on Antarctica, but there's no real stepwise difference. This is great news. When we just allow plus 3 degrees, so essentially following something close to the current NDCs, you can see that there's a big difference in the red curve. There's a big jump in the rate of ice loss on Antarctica, and it's because we're beginning to lose those critical ice shelves that fringe and apron around the continent. We're getting, for example, 15 centimeters of sea level rise just from the Antarctic ice sheet in the year 2100, which is about at a rate of sea level rise that is about 10 times faster than the rate of sea level rise coming from Antarctica today. So we've crossed a threshold somewhere between plus 2 and plus 3 degrees. What's happening is Here's a model simulation of the Antarctic ice sheet as it looks basically today. And I want you to just keep your eye on this sector of Antarctica. This is the West Antarctica, the West Antarctic ice sheet. And there's a very wide, very deep glacier here called the Thwaites Glacier that drains much of the interior of the West Antarctic ice sheet. These light blue colors that are seaward of these black lines, this is where the ice sheet ends and the ice shelves begin. So this is floating ice, this is floating ice, this is floating ice. These are the ice shelves. And you can see them fringing around much of the continent. So here's 1950. We're going to follow a +3 degrees C scenario following the current NDCs roughly. In +3 degrees in the year 2100 for the NDCs is conservative, by the way. Most recent estimates now are as high as +3.5. Here's 2100. And what you can see is that we're beginning to thin these ice shelves around the continent. Some have been lost entirely. We've got our 15 centimeters of sea level rise from Antarctica. And now when we go to 2300, very different picture. And we see that the Thwaites Glacier has basically eroded into much of West Antarctica. We would be potentially talking about 1 to 2 meters of sea level rise coming out of just the Antarctic ice sheet. So this would be additional onto all the other things that cause sea level rise: thermal expansion, glaciers, Greenland ice sheet, and so forth. Okay, so then to sort of wrap up what we've been able to test and look at, and this is an important message, is that once something like this begins to happen, and for example, the Thwaites Glacier begins to collapse and West Antarctica is retreating, can we stop it? And so what we do is we start down the path following the NDCs, and then we imagine that we can remove CO2 through carbon dioxide reduction. Somehow magically we'll have developed the technology to do this. And so we follow the NDCs, and then we say in the year 2050, for example, we start very rapid CO2 drawdown. What we find is that if we follow the NDCs, we trigger rapid ice loss, even if carbon dioxide reduction were to commence as soon as about 2060 to 2070. So once these processes begin, we lose those buttressing ice shelves. There's really no turning back, because the ice shelves can only regrow if the oceans are cold enough again to allow them to regrow. And once you put a lot of heat into the ocean doesn't cool down again quickly. So there's an important message here. Delayed mitigation in the very near term has a major effect on sea level rise for centuries into the future. Okay, then lastly, the numbers, for example, in the NDC scenario, +3 degrees C, 15 centimeters from Antarctica might not sound catastrophic. If we have a little bit of a longer term perspective, it's really the 22nd century after the year 2100 that the ice sheet in Antarctica really wakes up. In the high emission scenario, these are examples. In the year 2200, we would potentially be looking at 5 meters of sea level coming from Antarctica. In the year 2300, 10 meters of sea level rise coming from the Antarctic ice sheet. And if we think about what that would do, for example, to some areas in southern Sweden, everything we see in blue here is inundation of land. This is not storm surge, flood. This is inundation with 5 meters of sea level rise. And this is 10 meters in a high emission scenario. So to conclude, the most recent work, and this is something that just appeared in Nature just about a month ago, if we let global temperatures rise above 2 degrees C, we're significantly increasing the risk of triggering rapid ice loss from Antarctica, which for the Antarctic ice sheet would be irreversible and unstoppable. So the current NDCs and NDCs from this modeling perspective are not good enough. Overshooting the aspirations of any more than +2 degrees, even for just a few decades. So this is the overshoot point. We cannot have an overshoot, because if just a few decades go by above +2 degrees, we're worried about triggering these instabilities again that would be irreversible. So overshooting is not an option. And there's a lot of uncertainty in these numbers, exactly where that threshold is. would be much better off if we can stay closer to plus 1.5. And then lastly, the higher emission scenarios, if we were to go anything above the NDCs, for example, we would be talking about sort of catastrophic potential rates of sea level rise coming from the Antarctic ice sheet. And I'll conclude there.
Thank you so much, Rob, for those really excellent presentation and those really wise words. I hope people are filling the Q&A and the chat with questions that we can take in the discussion at the end. Thank you so much, Rob. We're going to move on to the next panelist. Vår nästa panelist är Ingeborg Pei, fältglaciolog från International Kryosfären Climate Initiative. Ingeborg, är du med? You can maybe du kan sätta på videon.
Hej.
Jättebra. Och Rob,
Ja.
det går bra att stänga av din video nu, om det är okej. Oh, sorry, Rob, you won't understand. Rob, you can turn off your video now, so well, perfect, thank you. Oh, no, Ingeborg. Ingeborg, we'd like your video back on, Ingeborg.
Okay, it seems to switch off as soon as I share my slides.
Okay, Pam, can you help?
No, it's okay. That's a function of her computer, so she'll simply need to show the slides.
Okay, that's
you're
great.
seeing my slides now?
Yes.
Great, okay.
Okay,
I'll turn my video off as well, so it doesn't look like it's me speaking.
Yeah.
Okay,
Just go
Rob,
into
if you
full
turn
screen
yourself
mode.
too.
There we go.
Okay, ja. Okej. Hej, tack alles där och hej allesammen. Glaciärer rymmer kanske inte lika mycket is som inlandsisarna på Grönland och Antarktis, men de var de största bidragsgivarna till havsnivåhöjningen under 1900-talet. Smältningen av glaciärer accelererar fortfarande idag. Det är viktigt att notera att glaciärer inte bara har ett betydande inflytande i fjällen där de finns, men också nedströms hundratals eller tusentals kilometer bort. Glaciärer och snö är viktiga i många länder, inklusive naturligtvis Sverige. Sötvatten från glaciärer och snö används för drickning, sanitet, bevattning och vattenkraftproduktion. Detta är särskilt viktigt under torra årstider, varmeböljar och torka. Glaciärer och snö stöder också skidindustrin, andra fritidsaktiviteter och turism. Smältning av glaciärer och förändringar i snötäcket kan orsaka faror som översvämningar, laviner och jordskred. I ett nötskal är glaciärer och snö av stor socioekonomisk viktighet. Vad händer med glaciärer under olika utsläppsscenarier? Dessa och följande grafer visar prognoser för glaciärer i olika regioner. Orange är ett overshoot-scenario som är lika med Parislöften. Och rött är extrem overshoot över 4 grader fram till 2100. De blå linjerna visar ett lågutsläppsscenario på 1,5 grad. När kurvorna når botten av varje diagram och värdet 0 betyder det helt enkelt att det inte finns någon is kvar. Låt oss först titta på tropiska glaciärer med bilder från Kilimanjaro i hörnet till höger. Tyvärr för de flesta av dessa glaciärer är till och med dagens temperaturökning på cirka 1 grad redan för mycket. Mycket få tropiska glaciärer kommer att överleva 1,5 grader. Låt oss gå vidare till glaciärer på mellanbredderna där isförlusten också accelererar. I dessa regioner kommer all isen att försvinna innan 2300 om vi följer scenarierna med höga utsläpp. Men lyckligtvis finns det andra vägar som vi kan välja att följa istället. Och om de globala temperaturerna förblir vid eller under 1,5 grader kan dessa glaciärerna bevara upp till 40-45% av sin massa fram till 2300. Liknande prognoser har gjorts för Nya Zeeland, Kaukasus, Mellanöstern och västra Kanada och USA. Och i Centraleuropa, om du tittar på den blå kurvan i diagrammet i den nedre högra hörna, kan vi även få någon återväxt av glaciärerna om vi stannar vid eller 1,5 grader. Låt oss nu se på Skandinavien och Sverige, där den södra toppen av Kebnekaise i bilden har tappat sin krona av Sveriges högsta topp på grund av smältning av glaciären som täcker den. Under de senaste 50 åren har glaciärens reträtt minskat höjden på den södra toppen med 24 meter, med reträtt av glaciären ungefär 1 meter per år sedan sekelskiftet. Om vi fortsätter att följa de högsta utsläppsscenarierna finns det ingen is kvar i Skandinavien på drygt 130 år. Men lyckligtvis, om de globala temperaturerna förblir vid eller under 1,5 grader kan vi bevara nära 20% av isen som vi har idag, vilket är mycket bättre än ingen is kvar alls. Låt oss nu titta på glaciärer i höjd och hög latitud. Där igen är skillnaderna mellan utsläppsscenarierna stora, och naturligtvis genom att följa scenariot med låga utsläpp i blått bevarar vi mycket mer is innan 2300 än med andra scenarier. Det är värt att notera att de höga utsläppsscenarierna i rött leder till en nästan komplett isförlust i de norra och södra delarna av Centralasien, där hundratals miljoner människor förlitar sig på denna värdefulla vattenförsörjningen. Slutligen, låt oss se på snö. Våra nuvarande observationer avslöjar att närvaron och uthålligheten av snö förändras över hela världen. Snösäsonger blir kortare varje år och snön täcker mindre mark än tidigare. I Sverige är de ekonomiska konsekvenserna av en minskning av säsongens snötäcke betydande. Mindre snö påverkar mängden och kvaliteten på flöden i floder. Mindre snö betyder också mindre skydd för övervintringsgrödor och vegetation från frost. Varmare vintrar leder till torrare jord som gör dem mer utsatta för skogsbränder, och slutligen påverkar mindre snö vintersport och turism. Det enda sättet att bevara så mycket snö och is som möjligt och skydda våra vattenresurser är att omedelbart minska våra utsläpp och följa en 1,5 graders väg. Tack för uppmärksamheten.
Tack så mycket Ingeborg för en spännande föreläsning. Och jag hoppas som sagt att många frågor kommer in i Q&A som vi kan ta vid slutet av presentationerna. Stort tack Ingeborg. Och we're now going to continue to the third talk, which is by Helen Finley, Plymouth Marine Laboratory. And we'll be talking to us about polar seas, the North Sea, Baltic Sea's long-term consequences of an overshoot. Do we have you there, Helen?
Yes, I'm just going to share my screen now, hopefully.
Lovely.
You can all see that.
We can. We're seeing your presenter mode at the moment. Yeah, beautiful. That's just what we want. It's lovely.
Fantastic. Lovely. Right, I'm going to leave my screen off, my video off, just because of bandwidth issues. So great, thank you very much for inviting me to talk to you today. The polar oceans are becoming warmer, they're fresher and more acidic. And this is amplified in the Arctic Ocean. These top two panels here, they're from the SROC report that Rob mentioned. These two panels show the Arctic surface waters warmed since the 1980s. And the greatest warming trend of about 0.5 degree per decade is occurring during the summer when the sea ice minimum is minimum, and that's this panel here on the right. However, there are still warming trends in some sectors even in the winter. You can see in the Atlantic region around north of Norway and Scandinavia, it's still very much a warming trend. The ocean warming is amplified by ice loss feedback on albedo. So white ice reflects heat, but dark ocean absorbs more heat. In turn, ice loss is amplified by increased ocean heat transport into the Arctic, particularly in the Atlantic sector, meaning that ocean warming and ice loss are interlinked and feed back on each other. Warming and ice loss also in increased river runoff, which causes freshening of the oceans, and this in turn impacts carbon and nutrient budgets with knock-on implications for the food web. All these aspects are significantly reduced under the low emissions scenarios, or the blue lines in these bottom panels, and compared to the high emissions red lines in the top panels. Ocean acidification is the process where carbon dioxide is absorbed into the ocean and reacts to produce a weak acid called carbonic acid. This alters the marine carbonate chemistry. Because polar oceans are colder and fresher, they're more susceptible to acidification as they have a lower ability to buffer changes in acidity, and the loss of sea ice is also allowing an increased uptake of carbon dioxide. A change in acidity can impact organisms on many different levels, but the most obvious one is that carbonic acid is essentially corrosive to calcium carbonate minerals. So any organism that produces carbonate shells skeletons, such as mussels, clams, oysters, or corals, are susceptible to these corrosive waters, making it more difficult for them to build and repair their structures, and more likely that any exposed structure will dissolve. The red on these maps shows the extent of these corrosive waters in the year 2100. So by the end of the century, in a high emissions or overshoot scenario, you can see that almost all of the Arctic and all of the Southern Ocean surface waters are going to be corrosive to these minerals all year round. If we can stick to the low emissions pathways or the Paris World Agreement of 1.5 degrees, you can see that nearly all of the Southern Ocean is prevented from becoming corrosive, and most of the Arctic with just seasonal patches becoming corrosive in the Arctic. However, in fact, already today, we see areas of corrosive water in the polar regions that appear seasonally and are causing damage to organisms. This is an example of a pteropod, which is a small free-swimming snail that is a primary food source for fish, including salmon. This is a recent study from this year where pteropods were sampled in the Canadian Arctic, and they were already found with these areas of pitting and dissolution on their shells in today's conditions. So a key take home is that acidification can only be reduced by reducing emissions. It's likely to take thousands of years for carbonate chemistry to return to its present state. And we know this by comparing past CO2 events, such as during the Paleo-Eocene thermal maximum, which occurred 55 million years ago. Here you can see the speed of carbon input today, which is shown in black, is occurring 10 times faster than seen in the event 55 million years ago, which is shown in red, when a mass extinction also occurred. It took tens of thousands of years for ocean chemistry to recover, and even longer for organisms. We also know that through modelling future scenarios beyond the year 2100, so here we go up to the year 2500, you can see that if we have zero emissions after the year 2100, in this example, pH is still only increasing very minimally in this low overshoot scenario world. Whereas if we can stick to a 1.5 degree world, we're seeing much less of an impact. Finally, we can look at a regionally relevant example of how these changes might impact fish species. So this is an example of cod. Freshening will change nutrients, and this will impact ocean productivity, so changing in plankton production and decreasing the food availability for fish species. Ocean acidification has been shown to negatively impact cod reproduction. So given that the Arctic is highly susceptible to acidification, this will prevent cod populations from moving northward, which is what we'd expect them to do as the ocean continues to warm and southern species move north. So this will result in cod being stuck between these pressures in a sort of sandwich effect. And a recent modelling study showed that these stressors put the fisheries at risk of collapse under high emissions or overshoot world scenarios. So to conclude, keeping emissions to a level equivalent to a 1.5 degree world is absolutely vital for minimising these risks to polar ocean ecosystems, which are very complex and multi-stressor environments, and that will protect the ocean ecosystems and the services that they provide us. Thank you very much.
Thank you so much, Helen, for an excellent talk and really very, very wise words in your conclusion. Again, I hope to make sure you're sending questions into the Q&A so that we can take them at the end for Helen. Nu kommer vi att fortsätta med vår fjärde panelist, och då har vi Gustav Hugelius som kommer att berätta för oss om tinande permafrost, 6 generationer med negativa utsläpp. Gustav, välkommen.
Tack så mycket, Alistair. Jag hoppas att ni ser min skärm. Okej. Ja, så jag ska alltså berätta om permafrost och vad som händer när permafrosten tinar. Permafrost är Mark som är frusen året runt finns främst i Arktis och i de stora taiga-regionerna i Nordamerika och Sibirien. Och när den tinar så släpper växthusgaser ut. Permafrost man brukar tala om det som en sovande jätte i klimatsystemet. Och det är en passande jämförelse. För dels så rör det sig faktiskt om väldigt stora områden. Permafrost på norra halvklotet täcker ungefär 3 gånger mer än hela EUs yta. Och det innehåller också enormt stora mängder av organiskt kol, gamla växtdelar som är frusna i den här marken och bevarade där. Ungefär 3 gånger mer kol än om man skulle ta all jordens vegetation ihop finns frusen i permafrosten. Och den här bilden ger ett ganska dramatiskt exempel på hur det kan se ut när permafrosten tinar. I det här fallet ser vi hur landskapet helt enkelt kollapsar när den massiva isen som finns i marken försvinner och man har ett helt annat landskap efter den tinande permafrosten. Det som händer är i stort sett att den globala uppvärmningen tinar permafrosten från sidan och uppifrån och så frisläpps det då växthusgaser när det här organiska materialet som tidigare var fruset och bevarat blir tillgängligt för mikroorganismer att bryta ner. Och det rör sig om både koldioxid och metan. Man får lite olika balans av olika växthusgaser beroende på hur miljön ser ut efter att det tinat. Och jag tänkte prata lite om tinande permafrost och overshoot som vi har pratat en del om här. Alltså när overshoot är när vi skjuter över temperaturmålet för att sedan gå tillbaka ner till målet med så kallade negativa utsläppsteknologier. Och problemet med den typen av scenario eller att ta den vägen helt enkelt är att många av de här naturliga systemen de kommer att förändras på ett sätt som inte är lätt att backa ifrån. Den röda linjen här visar ett overshoot-scenario där vi går över måltemperaturen och sen ner igen till kanske 1,5 grad. Medan den gröna linjen visar ett enligt oss då betydligt bättre scenario där man snabbt minskar utsläppen och helt enkelt stabiliserar på den lägre temperaturen direkt. För permafrosten så innebär overshoot, precis som det gör för inlandsisar och andra kryosfärskomponenter, att vi har problem med feedbacks från dem. Problem 1 är dels att permafrost ökar faktiskt själva uppvärmningen så att man kommer ännu högre än vad man kanske hade planerat. Och det är ju sant både för den röda och den gröna linjen. Men problem 2 är att förlusten av permafrost är nästan irreversibel. I alla fall på policy, som för oss människor på policyrelevanta tidsskalor så är den det. När den väl har tinat så kommer den kanske fortsätta släppa ut växthusgaser i flera hundra år efter att den har tinat. Och det här är någonting som vi projicerar, alltså det är på väg att hända, det kommer att tina om vi fortsätter att värma upp som vi gör. Men det är ingenting som bara är i framtiden, det händer redan. Det här är exempel från värmebölger som var i höga Arktis för några år sedan, inte den som var förra sommaren utan tidigare. Och där såg man några varma somrar i Kanada gjorde att permafrost som enligt modellerna skulle varit stabil i 70 år minst tinade redan då. Och man ser jättestora förändringar som händer redan. Det här ser vi tyvärr också över hela Arktis. Här ser vi en karta för permafrostutbredningen 2003 baserad på observationer och modeller. Och om jag trycker mig igenom här fram och tillbaka så ser ni hur den bara från 2003 till 2017 ändrar sig väldigt snabbt. Så vi ser redan nu hur den här uppvärmningen i Arktis snabbt påverkar permafrosten. Och den här upptiningen av permafrosten kommer att släppa ut växthusgaser som verkligen substantiellt minskar vår kvarvarande kolbudget för att hålla oss under måltemperatur av 1,5 grad eller 2 grader. Här ser ni 2 stycken staplar som visar den totala budgeten vi har för att hålla oss under 1,5 grad eller 2 grader. Och den rosa delen av staplarna visar hur stor andel som äts upp av enbart permafrosten. Så vi måste ta med det här i beräkningarna när vi då planerar framåt. Och det finns i dagsläget inte med i de underlagen som diskuteras i COP-sammanhang. Den goda nyheten är att utsläppen från permafrosten beror väldigt mycket på hur mycket och hur snabbt vi minskar våra utsläpp. Så om vi håller oss under 1,5 grader, då kommer permafrosten i slutet av det här århundradet motsvara kanske Indiens utsläpp idag. Men i de högre scenarierna så kan utsläppen från permafrosten skena och bli så pass stora så att de närmar sig Kinas eller USAs utsläpp under dagens förhållanden. Och så den här viktiga poängen med det långa tidsperspektivet. Permafrost är någonting som reagerar ganska långsamt, men det är också ja, det håller också på länge, alltså de negativa effekterna är också, de kommer att finnas kvar med oss. Så här ser vi kumulativa utsläpp av koldioxid vid slutet av det här århundradet. Om vi skulle låsa temperaturen vid +1,5, +2 och +4, så in i blå, röd och gul stapel. Och om vi då låser temperaturen där och inte har ytterligare ökningar så ser vi de utsläppen. Men det är det att eftersom permafrosten fortsätter att reagera länge efter att temperaturen har stabiliserats, så tittar vi längre, 200 år till, så fortsätter utsläppen att öka ännu mer. Och ni ser framförallt de höga utsläppsscenarierna, så även om vi stabiliserar 2100 så fortsätter permafrosten att släppa ut växthusgaser i flera hundra år till. Vilket då i praktiken betyder att vi förbinder många kommande generationer till att behöva använda negativa utsläpp för att hålla den här permafrostutsläppen under kontroll. Så att, vilket då verkligen pekar på liksom en generations rättvisa i att agera snabbt och inte binda sig vid hundratals år av negativa utsläppsteknologier. Tack.
Tack så mycket Gustav. Tack för en väldigt intressant och spännande föreläsning. Som jag sagt tidigare, se till att det kommer ställa frågor i Q&A som vi kan ta vid slutet av presentationerna. And we're now going to go to our fifth and final panelist. And we're going to hear from Dirk Knotts. And Dirk's going to talk to us about ice loss from the Arctic Ocean and effects on weather of going beyond 1.5 degrees. Dirk, the floor is yours.
Ja, tack så mycket. My Norwegian is better than my Swedish, but my English is even better. So I suggest I'll do this in English. And what I would like to talk about today really is the loss of Arctic summer sea ice. And given that you've all had busy days behind you, I thought I'd give you the really short summary up front, because all I want to say and all I want you to remember from today's presentation can actually be summarized in 7 words. And so if you remember those 7 words, you know basically 80% of what we need to know about Arctic sea ice loss. So Arctic sea ice loss in 7 words. It's real, it's us, and it's too late. And those 3 topics really are the ones I would like to cover today. And I would like to start, of course, with it's real. And in order to do that, I think the most obvious thing to do really is to look at 2 satellite images in comparison. And I've chosen here one from the year 1992, end of summer 1992, because always at the end of summer, after sunlight has been hitting the ice for 24 hours a day, the Arctic sea ice coverage, these ice flows of about 1 or 2 meter thickness that float on the ocean here, has reached its minimum extent. And in 1992, as you saw at the end of summer, still most of the Arctic Ocean is covered by sea ice. You wouldn't have been able to go through here with a ship easily. And 1992 was also the year where the big sustainability conference in Rio took place, and where policymakers from all around the world decided to now finally take care of this planet so that we can give it in all its beauty to the generations that come after us. What has happened since 1992 in terms of Arctic sea ice? This is how the Arctic looked like 21st of September 1992. This is how it looked like on the very same day last year. In terms of the area, this is about half as much as we used to have 30 years ago. And these ice flows that are left here are also only about half as thick as they used to be. And I don't want to do too complicated math here today, but reducing the area by 50% and the thickness by 50%, we see immediately that in terms of volume, we have about a quarter left. And what will happen to this last quarter, I'll talk about a bit later. So it's clear the sea ice loss in the Arctic is real, and it's possibly, and I would even say probably, the most obvious and best documented large-scale change on our planet related to global warming. The second point I would like to bring home today is that this sea ice loss really is caused by us. And for me, the simplest way of showing that is simply based on looking at measurements, and 2 time series of measurements. One is simply how much sea ice do we have in the Arctic in terms of sea ice area. And the second time series is how much CO2 emissions have we humans put into the atmosphere? And if we just take these two time series and plot them against each other, this is what we get. From the beginning of the satellite record, and we can extend this actually a couple of decades further back, which just follows this trend, until last year, we do see this very clear linear relationship between how much sea ice we have in the Arctic and how much total CO2 emissions we humans have put into the atmosphere. And we see the same linear relationship in every climate model simulation, and we can explain it conceptually. So it's not just a correlation, but we can show that there is causality between these two numbers. And we can also calculate the slope of this line, which then shows us how each of us contributes to the loss of Arctic sea ice, because the slope is that about 3 square meters of these ice floes of about 1 meter thickness are being lost for each ton of CO2 emissions. And so that allows us to calculate how each of us currently is melting ice in the Arctic by the various activities that we carry out. So it's not anything abstract anymore, climate change, but it's something that can be very concretely linked to our actions. So sea ice loss is real, it's us. And unfortunately, we've now come to the conclusion that it's too late. And what I mean with that is that it's become too late probably to still rescue this last quarter of Arctic summer sea ice volume. There has been too much ice loss over the past few decades, and the ongoing climate change is developing too rapidly to make it realistic that we can still rescue this last quarter of Arctic sea ice. And I would like to convince you of that by 2 lines of arguments. The first one is simply extrapolating this observed trend, because we know from climate model simulations that this linearity will simply hold until the future. And if we just take this middle line here, that shows us at which CO2 emissions or at which temperature threshold the Arctic will be ice-free in most years. And that will happen at some point between 1.5 and 2 degrees global warming, and at about another 800 gigatons of CO2 emissions. But we also have this sort of lower line here because some summers are warmer than other summers. So we do get sometimes extreme minima in Arctic sea ice. And this is this line here that shows when the Arctic gets ice-free in some years. And that will happen roughly at a global warming of about 1.5 degrees. Because when I say ice-free, we mean a sea ice area of less than 1 million square kilometer, which means practically ice-free for all practical purposes, including the ecosystem of the Arctic. And the problem is similar to other tipping points. Once we've lost the summer sea ice in 1 year, the ecosystem that is connected to the summer sea ice will not survive this single summer, and it will be gone forever, basically. And it's extremely unlikely that we will be able to keep global warming so below this threshold here, below this threshold where we lose Arctic sea ice at least in some years. Which is also depicted here once again, is this trajectory on which we are currently, and how the Arctic will look like in the seasonal cycle, whether it's ice covered all year round, or whether we will have some years that are ice-free. So this is just from the conceptual model, but we do find the same picture in these very complex CMIP6 Earth system models, where we just published a study last year where we concluded from these most recent climate model simulations that in the vast majority of the available CMIP6 simulations, the Arctic Ocean becomes practically sea ice free in September for the first time before 2050 in every emission scenario that we think is realistic, even the ones that keep global warming long-term below 1.5 degree global warming. It's too late to still rescue the Arctic summer sea ice in every year, but we can still prevent that it's being lost in most years. And now what are the implications finally? In terms of weather, the good news is probably that the current standing, or where we currently stand in terms of our science, is that the impact of Arctic sea ice on weather patterns is comparably small to other fluctuations we have in the climate system. So that the impact on weather patterns is probably not as large as we thought a couple of years ago. But maybe, and that's what I would hope for, the impact of this loss of Arctic sea ice really is a warning signal that is so loud that I would hope that everyone can hear it, because it will be the first landscape that we lose on this planet related to global warming. And it's an incredibly beautiful landscape, and it will not be the last landscape we use. And what I often think about is what this loss of this beautiful landscape up there actually does to our culture, to the way we see our planet, to the way we think there is something beauty, something amazing in the Arctic. And losing that and knowing that future generations will not have that landscape anymore, I feel is a consequence of global warming that we talk about way too little, because it's the consequences for our cultural beings that we are as humans. And so to summarize, for each ton of CO2 emissions, the area of Arctic sea ice in summer decreases by 3 square meters. The Arctic will be practically sea ice free in September for the first time for future CO2 emissions of 800 plus minus 300 gigatons, which will be at the warming of 1.7 plus minus 0.4 degrees centigrade, and thus probably before 2050 in every emission scenario. We can still prevent, however, that the ice-free state becomes the new normal. And as for every presentation that we've heard so far, the ice loss will only end once anthropogenic global net emissions of greenhouse gases drop to net zero. The good thing is Arctic sea ice loss will actually end there, but we've also seen in some other presentations today that in other ice systems, there are tipping points that if we don't drop to net zero very rapidly, the ice loss will still continue long, long afterwards. And with that, I thank you very much for your attention, and I'm happy to take any questions.
Thank you very much indeed, Dirk, for that really great talk. I actually calculated that I'm responsible for 1,500 square meters of Arctic sea ice loss, just as one individual, based on the number you just put up on the slide. And it's a chilling thought that we are responsible for this. It would be great if the panelists would turn their cameras on. Thank you very much. We do have a lot of questions in the chat. I'm going to try and distribute them a little bit. So I hopefully will ask questions to each panelist. And I'll do my best to get through as many as I can. I ask the panelists to answer briefly as they can so that we can get as many questions as possible. And the first question is for Robert, and this is from Jonas Ikander. Was the maximum rate of sea level rise? Was the maximum rate of sea level rise after the LGM? What was, I think, is. Thank you.
Yeah, so there have been pulses of sea level rise since the LGM, and they're on the order of multiple centimeters per year, but it's really not comparable to the current system because a lot of that was coming from the Laurentide ice sheet covering North America. And of course, there was a Fennoscandinavian ice sheet that was melting. We don't know exactly how much a modern sized Greenland ice sheet and an Antarctic ice sheet, something that looks like today's system, was contributing to sea level rise in the past. That is an area of study. The paleoclimate community are working on trying to give us better numbers. But the magnitudes are important. You know, the fact that sometime during the last interglacial, the last time that the global climate state was comparable to today, pretty close, we think, to the early 21st century sort of global mean temperatures, the estimates are 6 to 9 meters of sea level rise relative to modern. And the thinking is that a lot of that, about 6 meters of that sea level rise, actually occurred within a few thousand years early in the interglacial. And it's thought that up to 6 meters of sea level rise within a few thousand years early during that interglacial was mostly coming from Antarctica, because we don't think Greenland's contribution wasn't until much later. So those are, we wish we had more firm estimates and numbers from the paleo scenarios in terms of the rates, but the magnitudes, I think, are telling an important story on their own, that the ice sheets are indeed sensitive. And the thinking was that those sorts of sea level rises could only occur over multiple thousands of years. And now I think the thinking is that now we're thinking more sort of century sort of time scale, which means that decade by decade, would be looking at rates of sea level rise potentially from Greenland and Antarctica that would become unmanageable from a sort of coastal engineering standpoint.
Thank you, Roberto. I'm going to go to a question now for Ingeborg. And this was in Swedish. Ingen is som 130 år i Skandinavien. Kan du utveckla det lite? Vilken is talar vi om? Vad får det för effekter till exempel runt Kebnekaise? So no ice in 130 years in Scandinavia. Could you develop that somewhat? And what are we talking about? What are the effects, for example, around Kebnekaise?
Yeah.
And this is from Leif Östman.
Når jeg sier is i Skandinavien, så snakker vi om is i Norge og i Sverige. Og effektene blir jo de samme i Sverige som i andre land. Da tenker jeg først og fremst i Sverige på turisme og skitindustrien. Det kommer til å bli tørrere, som kan årsake brenner. Det kan ha effekter på rennæringen, for eksempel, med mindre beitemark som tilgjengelig. Men først og fremst så blir det jo vattenkraftproduksjon som kommer til å se effektene av det. 80% av elproduksjon i Sverige fra vattenkraft i Nordland, så det klart at det kommer til å få effekter på det.
Tack så mycket, Ingeborg. And I have a question from Dirk, an anonymous attendee. And what is the difference between summer ice and other ice? Could you clarify that, Dirk?
Sure, of course. So at the moment, we do have sea ice all year round in the Arctic. And so we do have ice in winter and in summer. And when I talk about the summer ice, what I mean is that during summer, the Arctic will become sea ice free. And the ice type that then disappears is the ice type that we refer to as multi-year ice, which is an ice flow that developed in winter, survived the summer, and is still there in the next winter. And it's this ice that, for example, carries much of the ecosystem of the Arctic, because it's there all year round and things can develop. If the ice disappears during summer, the ice type we will only have in the future is so-called first-year ice, which is ice that forms in the winter and then melts again in the following summer. And so in some sense, and that's also what I try to communicate to all the students we have, we might really be the last generation that is able to investigate this multi-year sea ice and the ecosystem connected to it, and the physics of this multi-year ice, because this ice type will in the future no longer be there.
Thank you, Dirk. And now I actually have two more questions here, and we've got 1 minute, and they're both for you, Robert. So I'm going to ask you for very short answers so both people get an answer. This is from Christian Dieterich. Considering the fingerprints of Antarctic contributions, would there still be the same order of magnitude of SLR in Sweden? And please specify what SLR is. And turn your mic on as well.
So this is a fantastic question. The point is that sea level rise will not be the same for everyone around the world. When the ice sheets lose ice, they lose mass, and that affects the Earth's gravitational field and even our pole of rotation. And we can produce, the geophysicists can produce maps of where sea level rise is going to be above the global average and where it might be a little bit less than the global average. And the maps that I showed of what 5 meters or 10 meters of sea level rise looks like for Sweden did not take that into account. But that guidance is fully available in the SROC. So the IPCC SROC report provides a regional overview of what sea level rise will be. And what you might find for Sweden is the combination of these so-called fingerprints, the gravitational effects, and the fact that Sweden is still rebounding from the last time that there was ice covering Scandinavia, that it would be a departure from the global average and perhaps a little bit less. I will tell you that Boston, for example, my hometown, feels 25% more sea level rise than the global average when the sea level rise is coming from the loss of Antarctic ice. but Boston only feels about 35% of the global average of sea level rise if that sea level rise is coming from Greenland. So we have to take those things into consideration. So the person who asked the question can look to the IPCC SRAC report online and see these maps, and you can look to your hometown to see where you might be looking at more or less than global average of sea level rise.
Thank you, Roberto. I'm under strict instructions. I need to end the session on time. I'm going to end it now. There is a question from Eric Huss about when we feel the Greenland ice will be lost. I would appreciate if, Roberto, you would go in and answer that in the Q&A so that everyone can see the answer to that. But we now do need to close the session. Thank you, and give a great big distant Zoom applaud to our panelists today. Please be clapping in whatever silent room you happen to be in. Thank you very much for being part of this meeting today. Goodbye.